So we're going to just start with talking about the different graphs of polynomial functions. So what is special about a polynomial is that it's one of those graphs where there are no gaps. Basically, you can draw it with one stroke of like your pen. You don't have to lift your pen off of the paper, and we call that continuous. And there are no sharp turns in the graph. Like absolute value functions, those have a v. There's a very sharp point. Polynomials don't do that. They're curved the entire way. So there are two basic shapes. There's the shape on the left and then the one on the right. So the shape on the left is when you're the highest exponent, which is called the degree of the polynomial, even. So if the highest exponent is an even number, then it's going to look like the number on the left. If the highest exponent is odd, it's going to look like the graph on the right. So there are two basic shapes, and then there can be some variation in the middle of those. Sometimes, and this is why I like polynomials, is you can get some really interesting shapes. But whatever happens in the middle, sometimes there's like extra curves in there. So it may not be completely flat. There may be other curves going on, but the basic shape when you zoom out looks the same. So this brings us to the leading coefficient test. So the leading coefficient test determines the end behavior of a polynomial. And we call this end behavior because those are essentially the ends of the graph. And it's like, what happens when you really zoom out of your graph? What does it look like? Because that's what we care about, are the two basic shapes. So to use the leading coefficient test, you start with your polynomial, and you start by determining the degree of the polynomial, which is, as I said, is the highest exponent. It's either going to be even or odd, and that gives you your two basic shapes, the same shapes that we have here. So you're looking at that degree so that you can determine your basic shape. And then you're looking at the coefficient of that term. Oops, went too far. The coefficient of the term, which is the number in front of it. And that number basically tells you what happens to the right side of the graph, whether it's going up or going down. So there are four choices. And on the top row, I have the odds, bottom I have the evens, the left side is positive, right side is negative. So if you have something that has an odd degree and the coefficient in front of it is positive, it's going to look like that shape that I have drawn there for the end behavior. And then, like I said, in the middle, there could be some squigglies and some other things going on. If you're to describe that in words, you would say that it falls to the left and rises to the right. When it's a negative coefficient, it basically reflects it because of that's a property of a transformation. The negative flips it, reflects it across the x-axis, so it makes it upside down. So that same shape with an odd degree and a negative coefficient now looks the opposite. So now it rises on the left instead of falls, and it falls on the right instead of rises to the right. So it kind of flip-flops. And the same thing happens if you have an even degree. If the coefficient is positive, it opens up so both sides rise. And then if that coefficient in front is negative, then it opens down and both sides fall, essentially, if you were to describe it in words. I always prefer to draw a picture rather than trying to describe it in words. So we're going to start by actually sketching end behavior and then also talking about transformations at the same time. So here I have sketch the end behavior for y equals x to the fifth and describe the transformations below. So our exponent, our highest exponent is 5. So we say the degree is 5, and this is an odd number. And because the coefficient in front of that degree, the leading coefficient is 1, because there's no number, that's positive. So anything that has an odd degree and it is positive is going to look like this for the end behavior. So that is the basic shape. And then these transformations occur to the basic shape, shifting it left, up, down. The same transformations that we saw last week, they still apply here. So last week I had talked about how when we're looking at transformations, that degree or the exponent doesn't really matter. What matters happens, to the x, whether it moves left or right, that sort of thing. So that's the same thing here. So if we're looking at the top left, I have f of x equals x plus 1 to the 5th power. So we have something added to x, and anything we do to x shifts left or right. And it always does the opposite. So because that's a plus, this means we are going left 1 unit. So we're doing the opposite. Instead of moving towards the positive, we're moving towards the negative. The difference from this to the one on the right is that the plus 1 is not in parentheses. So that's not happening to the x anymore. Now that's happening to the y. And when that plus 1 is happening, that's an up or down. And then that one, it does follow whether the sign is positive or negative. So that is up by 1 unit. So bottom left, we have f of x equals 1 minus 1/2 x to the 5th. So traditionally, we want the highest exponent part first, but it doesn't really matter. But what matters here is that we have a coefficient in front of x to the 5th. So the negative here is telling us that we are reflecting. And then the 1/2, that number is telling us that we are shrinking because we have a number between 0 and 1. So those are the ones that kind of flattened it out and made it fatter, so to speak. So that gives us a reflection across the x-axis. And then we are shrinking by 1/2. Or sometimes they'll even say the vertical stretch of 1/2, but you're basically shrinking it down. So you might see the word stretch instead of shrink. It's the same thing. I just use shrink to indicate kind of what's happening to the graph, that it looks like it's getting flatter versus being stretched out. Now the one on the right, this is another one where we have these parentheses. It makes a big difference because we have this negative 1/2 in front. So that is the same as the reflection across the x and the shrink by 1/2. But then we also have this plus 1 in there, which is the left 1 unit. So we have both transformations on the left side combined into one. So we have a reflection across the x. We have our shrink of 1/2. And then we have moved left by 1 unit because of the plus 1 inside those parentheses. So there's 3 transformations occurring on that bottom right one. All kind of, you can have these different combinations and they do different things to the graph. Yes, yeah. And you would use your, you would compare it to this x to the 5th, which you would consider the parent function, basically. For a polynomial, whatever your highest degree is, whatever your degree is, that would be your parent function. So if it was to the 6th, then you would use x to the 6th. If it was 3, it would be x cubed. And you just use the most basic, if you had just one term with that exponent, that would be what your parent function would be that you would compare it to. Just gotta wait. Desmos is being a little slow today. Might be my internet. Okay, so our parent function is y equals x to the 5th. So it looks like that end behavior that I drew. It looks like a cubic, even though it's x to the 5th. What happens is the higher the exponent, it kind of gets a little narrower. So like if we looked at that last one that we did, y equals, we have a negative 1/2 in front, and then we have in parentheses x plus 1, and then to the 5th. So you can see the reflection that the blue is now upside down from the red. So you can see that pretty clearly. The 1/2 is a little harder to visualize because of the fact that it's also kind of shifted and everything. It's hard to see, but it is kind of smushed down a little bit. And then you can see that it's moved left 1 because you can see that out of those 3, it's marked 3 points here. but the one in the middle has been moved over to the left by 1. And so you can see that we have that reflection, then we have that 1/2, and then we moved by 1. And I can just get rid of this +1 so you can see, let's actually get rid of the -2 so you can see that what the 1/2 does. So 1/2 is a very small, it doesn't make a big difference, but you can see how it kind of flattened it a little bit. It kind of shrinked it down. Each y value is lower than it was originally, or when you're in the negative, it's kind of close to 0, and maybe each of them a little smaller, which is why we call it kind of a shrink. But visually, it's very hard to see that, which is why it's also good to understand what those numbers do, because you wouldn't necessarily be able to figure that out from the graph alone, what it did. So you can see how it moved it over again by another 1. So now it's been moved over 2 spots from the original that was also reflected and shrunk a little bit. So here we're going to just describe the left hand and right hand behavior of these polynomials. And we're going to do this basically just off of the degree and whether that coefficient for that is positive or negative. So first one left, we have f of x equals 2x squared minus 3x plus 1. So the highest exponent is 2. Oops, I forgot that I was still the highlighter. The highest exponent is 2, which is even. And then our coefficient here is 2, which is positive. So we have something that is even with a positive coefficient. So that matches an end behavior of a regular quadratic, which we've seen quadratics in section 3.1, where they focus on quadratic equations. So it's going to be opening up, both sides go in the same direction. On the top right, we have 1 minus x to the 6th. So we have, again, our even exponent, but then we have a negative in front. So that's going to reflect it upside down. So it's going to basically look like a frown instead, because that negative reflects it upside down. Bottom left, we have f of x equals 8 plus 1/4 x to the 5th minus x to the 4th. So you're looking for the highest exponent. So that's going to be the 5, which is odd. And then we have a positive number in front of that term. So we're looking at that particular term with the highest exponent. What happens to that number? So that is a positive in front. So that gives us our end behavior. That looks like this. Looks like the graph that we did in Desmos before it got reflected. Then bottom right, we have f of x equals 1 minus 0.5x to the 5th minus 2.7x to the 3rd. So again, our highest exponent is odd, which I was just about to write even as I said odd. And we now have a negative leading coefficient because we have a negative 0.5 right in front of that x to the 5th. So that's where we flip it upside down. I was trying to squeeze that in. Let me put that over here. So that's where we get that reflection, and it flips it upside down. Real zeros of polynomial functions. So if you have a polynomial and n is our degree, that highest exponent. So everything that we do with a polynomial, we're caring about that degree, that highest exponent there. The function has at most n real zeros. So if it was exponent of 4, there should be 4 or less, 4 fewer real zeros. And I say it could be fewer than 4 because you might have some imaginary zeros as well. But the maximum that you can have is the same as the degree. So you can't have any more than 4 if the degree is 4. Then the function has at most n minus 1 turning points. So if the degree is 4, then there may be 3 turns in the picture, but that at most 3 turns. There could be fewer than that, but there won't be more than that. Then given that we have some polynomial, and let's say b is a 0 of the function. So What that means is that b, x equals b, is a solution when that function is equal to 0. So when you set your equation equal to 0 and solve for x, you get zeros. That's why they are called zeros. And so they are solutions to that equation. What is also special about this is when we factor things, we always have to set it equal to 0. Like when we were factoring quadratics, we set our equations equal to 0 to solve those. So what that means is that when you get a 0, then x minus b is a factor. You're also getting factors. And the thing is, the factor has the opposite sign. So if you have a 0, 3, your factor would be x minus 3. It's everything with that x, we have the opposite sign, just with the transformations. Now, if your value that you got your 0 is a real number, not a complex number, that means it's also an x-intercept. So when you're solving for zeros, you're getting solutions, you're getting factors, and you're getting x-intercepts, as long as they are real numbers and not complex numbers. So you can get a lot of information out by setting your equation equal to 0 and solving for x. It gives you a lot of valuable information. And on our assignment, there's questions about factoring the polynomial and then finding the zeros. So when you go into like section 3.3, 3.4, it will show you how to do that for things that are like really high degree, and it'll show you how those are related. That when you find solutions where it's 0, you're also finding the factors and how you can write those things. So repeated zeros. So it's possible that you have a number that shows up more than once. Like you might be factoring it and you have a factor that shows up more than once. And so we call that a repeated zero. If you have something that's factored, and let's say like we had some quadratics where you factor and you get like x minus 2 squared or something like that, and you have some exponent on it, that means it's a repeated zero, that it shows up more than once when you factor. It's the same thing as like x minus 2 times x minus 2. So that tells you if it's repeated, it has a thing called multiplicity, which is basically that exponent. So if it's x minus 2 squared, the multiplicity is 2 because that's the exponent. It's basically how many times does that 0 show up when you solve. You know, sometimes you can solve and get the same number, or you factor and you get the same thing show up more than once. It's basically the multiplicity is how many times did that show up when you factored. What's special about the multiplicity is what it does to the graph. So if it has an odd multiplicity, so if it only shows up once or maybe it shows up 3 times, the graph crosses the x-axis. So I'm going to just kind of demonstrate what that would look like. So if I had like a 0 of -2, with an odd multiplicity, it just means that my graph goes through that point. It crosses the x-axis. Now, if it was even, so let's say that 0 showed up twice, or maybe it shows up 4 times, that same 0, what happens is it kind of bounces off. So it doesn't cross the axis, it bounces off, and it kind of bounces back up the direction it was going, or it might be coming from below and going back down. So this is just kind of gives you an idea of what these things what they can do to a graph. This will make more sense once we actually kind of graph some of these things. But like the k is even, it looks like a quadratic, so that's why that even number, it always kind of looks like a u, you know, and the odd always looks kind of like a cubic, where they're going kind of in the same direction. So they have the same kind of basic shape. Okay, so here's an example. We have f of x equals 81 minus x squared. So this is a quadratic. And we know how to factor quadratic equations or solve for quadratic equations. So we're going to find all of the real zeros and then determine whether the multiplicity of each 0 is even or odd, and then determine the maximum number of turning points of the graph of the function. So we're doing 3 things here. So we'll just go in order by finding all of the zeros, and I'll just kind of color code these. So when you find the zeros, you set your equation equal to 0 and then solve for x. So we have 0 equals 81 minus x squared. The easiest way to solve this is I can add x squared to both sides so that I have x squared equals 81. And then I take the square root. And when you take the square root, we get a plus or minus. So we get, and then the square root of 81 is, first I'm going to write plus or minus square root of 89. And that equals plus or minus 9. So we have two zeros here, and they're real zeros because they're not imaginary numbers. So we have -9 and 9 as our real zeros. And our exponent, the highest exponent, is 2. So our rule said we couldn't have more than that number of zeros. So we have at most 2 zeros, and we have exactly 2 zeros. So I wouldn't get 3 out of here. It's possible I would get 1, but they're the same number. But I'm not going to have more than 2. So I got 2 zeros out of here. So in the next one in purple, determine whether the multiplicity of each zero is even or odd. So each of these zeros showed up only once. When we solved, we just got one -9 and one 9. So because they're listed one time each, that means that they have odd multiplicity because 1 is an odd number. What this means if we were to graph this is that the graph would go through these points on the x-axis. It wouldn't bounce off of them. Now the last one, determine the maximum possible number of turning points of the graph of the function. So that goes back to the degree, the highest exponent. So our degree is 2, and the maximum number of possible turning points is always 1 less than that. Let me rewrite my x, maximum number of turning points. It's n minus 1, so that's going to be 2 minus 1, so we're just going to have 1 turning point. It's going to just have 1 curve in the graph at most. So I'm going to graph this. We have f of x equals 81 minus x squared. And then I'm going to have to zoom out because you can't really see it. A really tall graph. There we go. Okay, so the zeros are on where we cross on the x-axis. So we have -9 and 9. And because those had odd multiplicity, it crossed and went through. It didn't bound those points. So you can see that the graph just goes through those points. Our degree was 2, which left us with a turning point. Maximum number of turning points is 1. And you can see there's only one spot where the graph turns and changes direction. So that's sort of like, this is part of analyzing a function or analyzing a graph. You're taking the equation and then you're kind of analyzing, well, what does that do to the graph? And then you can even look at the graph and kind of verify these things. So I have another one here. This one is a little more complicated here. So we're doing the same things. We're going to first find the zeros, then determine the multiplicity, and then determine the maximum number of turning points. So we have f of t equals t squared times 3t squared minus 10t plus 7. So to find the zeros, which again I'm going to do in red, you set that equation equal to 0. Now for something like this, factoring would be the best bet here. And so t squared is just t times t, so I'm going to just write that. And then I'm going to want to factor the 3t squared minus 10t plus 7. So let's see, 3t times t will get me 3t squared. And 7 times 1 gets me to 7. if I make them both negative, and then I put them specifically in the locations I did so that I can get them to add to negative 10. Because the inside parts, when I multiply out, will be negative 7t. The outside parts will get me negative 3t. That adds up to negative 10t. So I factored that quadratic. Now when we're finding the zeros, we're setting each of these equal to 0 and we're solving for t. So I have t equal to 0, t equal to 0. This gives me 3t minus 7 equal to 0, and then t minus 1 equal to 0. So when I solve 3t minus 7 equals 0, I get 3t equals 7 after adding 7 to both sides. And then you divide both sides by 3, so we have t equals 7 over 3. Then when I solve t minus 1 equals 0, we got t equals 1. So we have 4 numbers here, but one of them shows up twice. Our zeros are 0, 7/3, and 1. The next would be the multiplicity of each 0. So 7/3 and 1 only show up once when I'm solving, so that's odd multiplicity. So this is odd, and this is odd. However, when we solved, we got t equals 0 twice. Because basically it had t squared, and if t is 0, that's 0 squared. It shows up twice, so that is even multiplicity. What that means is that when we graph this, it's going to bounce through, it's going to bounce off of 0 on the x-axis, and it's going to go through 7/3 and 1. Lastly is to determine the maximum possible number of turning points of the graph. So we have, when we solved, we got 4 numbers here. Our degree here is 4. You can also see that because when you multiply here, if you multiply this through, you would get 3t to the 4th minus 10t cubed plus 7t squared. So your highest exponent is 4. So the degree is 4. When you see we solved, we got 4 numbers, but really only 3 zeros. So that's why we say the maximum number of zeros is equal to the degree, but you could have fewer than that. Then the maximum number of turning points is 1 less than that. So the maximum possible turning points is 3, because that's 1 less than the degree. So we should have 3 points where this kind of curves, the curve kind of changes direction. So I'm going to pull up Desmos and graph this function. And I can use t in Desmos and it's going to be fine. It's going to just assume it's x. So we get t squared, and then in parentheses 3t squared minus 10t plus 7. Okay, so now, because I had zoomed out for that other graph, now I'm looking, let's zoom in. Okay, so now I can zoom in a little bit more. So when I multiplied it out, our highest degree is an even number, so that means it's going to open up or open down in the same direction, and our coefficient was 3, which is positive, so that's why this is opening up. Now our zeros are, if I click on the graph, they're marked, so we've got 0, 1, and then 7/3 or 2.33 as it shows up on Desmos. So we have those 3 zeros. Now because 0 showed up twice, I said that it bounces. And you can see that when it goes to 0, it bounced back up. It didn't cross that one. But 1 and 7/3 were odd multiplicity, so it did go through those and cross the x-axis. And then the maximum possible number of turning points was 3. And you can see there are 3 places where we change direction. We change direction at 0, where it bounces back up. Then at this point that it has marked, we're changing direction and we go back down. And then it marked another spot on Desmos where we're changing direction a third time and going back up. So we turned 3 times for this graph, which was 1 less than the degree. Okay, so now this is something different. So it says find a polynomial function that has the given zeros. So one thing, and I'm going to go back to the slide where I was talking about the zeros. So if you get a 0, you can use it as a factor, and I mentioned that it goes in the opposite sign. So if the b is positive, it's going to be x minus that number. If you have a negative 0, it's going to be x plus. So we're going to use this by taking the zeros and then writing the equations. So it says find a polynomial function that has the given zeros. And so the first one on the top left is -2 and 5. So I'm going to start by writing this in factored form by basically doing x and then the opposite of the sign. So if it says -2, that'd be x plus 2. And then it says we got 5, so that's x minus 5. So that would be the factored form. And so the zeros can be written as factors by kind of working backwards from when you factored a polynomial. You're kind of working backwards and writing them in the other direction. And then we generally want these multiplied out. So this would give us x squared. And let's see, 2 minus 5 minus 3x minus 10. So you factor that, or you basically take the zeros, you write them in factored form, and then you multiply it out, and that gives you a polynomial function that has those zeros. And I'm going to bring up Desmos to show you that. So we have f of x equals, we got x squared minus 3x minus 10. And so our two zeros were at -2 and 5. So you can see on the graph, -2 goes through the x-axis, 5 that goes through an x-axis. So those are our two zeros. And so we basically just translated those and we got an equation that has those zeros. So this one on the right, we have zeros of 0, 1, and 6. So if it has a 0 of 0, you just write x, because the x plus 0 or x minus 0 doesn't really mean anything. Then we have x minus 1 and x minus 6, because those are the opposite sign. And I'm not going to bother multiplying these out because, especially the one on the bottom, you have 5 zeros there. So that's going to have, multiplying it out is going to be really, really messy. So we're not going to worry about that. We're going to just leave it in factored form. But I just want to demonstrate that how you can do this. So the bottom one, if we have a 0 of -2, then we write that as x plus 2. Then we have one of -1, so that's x plus 1. Then we have 0, which is x, and we usually write that one in front. It just looks nicer in front than rather in the middle, because it kind of can look confusing. Then I have 1, so that's going to be written as x minus 1, and then we have 2, which is written as x minus 2. I'm going to actually leave myself some more space on the left. I'm going to put that x part there. So this, if I multiplied it out, we have 5 zeros, you would get something that's x to the 5th, and it would take a long time. It would be very tedious to multiply that out all by hand. So that's why I'm not going to do it. Now, I left these are a little more tricky. So that's why I put these on their own. So we have 4. It's the same thing. We're going to write using the zeros. We have 4 plus the square root of 3 and 4 minus the square root of 3. So when we write these are going to be kind of gross, and I'm actually going to multiply these out, or I'm not going to multiply the one on the right necessarily, but the one on the left for sure. So this is where it gets tricky, because we have x minus, and then you're taking the opposite sign. So if I'm going to do 4 plus square root of 3, it's going to be minus 4, and then also minus square root of 3, because you're taking the opposite sign when you put it in the factored form. Then the second one, it's 4 minus the square root of 3. So again, I'm taking the opposite sign. So that's going to be x minus 4, but now it's going to be plus square root of 3. So when you have things that might have like the imaginary number with them or square roots, you have these sort of, you need to take the opposite sign of everything that is with the 0. For something like this, we don't like to leave it in this form because of the square roots. So if you have something like this, you do need to multiply it out. And that's where it gets to be more work. So this is where I'm going to make a table of values. So I'm taking that first factor, and then I made it across, and then I'm going to take the second one, and I'm going to go vertically, and I'm going to just multiply each element and kind of fill in this table here. So x times x gives me x squared. Then I'm going to go x times -4, so that's minus 4x. X times negative square root of 3 is negative square root of 3x. Now I'm going to multiply the next row with each column, so I get negative 4x. Then negative 4 times negative 4 is 16. And negative 4 times negative square root of 3, those negatives cancel, and I get 4 times the square root of 3. Bottom row, I have square root of 3 times x. And then I have square root of 3 times negative 4, so that's negative 4 times the square root of 3. And then negative square root of 3 times square root of 3, so the square root of 3 times square root of 3 is 9, so, or that would give me square root of 9, which is 3. So the square roots just cancel, and I just end up with negative 3. Now, our things with the square roots actually end up canceling in this case. We have negative square root of 3x and a positive square root of 3x, so those actually add up to 0. Then I have a 4 square root of 3 and a negative 4 square root of 3, so that also adds up to 0. And this is why when you have things with square roots, you do want to multiply them out, because it actually will make it look nicer, even though it does take a little bit. So I now need to take everything I have in black that I haven't canceled. So I have an x squared. I have a negative 4x and a negative 4x. Those add to negative 8x. And then I have a 16 minus 3, which is 13. So this comes out to x squared minus 8x plus 13. And so in this case, we definitely want to multiply it out because it's easier to read than when we had it in factored form. Now the one on the right here, this is actually quite easy. So it says that our 0 is negative 3, so that's x plus 3. Now the thing is, it specifies degree 2, so that means we need to have 2 zeros. So we don't have another 0, so that means this must be a repeated 0. And so we just put a 2 on it in order to make sure that we have it listed twice, so that we do have 2 zeros there. So if it had told us it was like degree 5, we need 5 of them, and they only gave us 1 number, so the other 4 must be the same number, which mean an exponent of 5 on there. So when it tells you the degree, that means you need to have that many numbers of zeros, and if you don't, you just have to add those extra zeros in as exponents, so that you have that until you've reached the degree. All right, now the last thing that we have is the intermediate value theorem, and actually this is, you don't really need to use this at all in this course, but we cover it because it's something that's needed for calculus and not covered in pre-calculus. So there are some things in this course that are covered that are needed for calculus that aren't touched upon again until you get to calculus, and this is one of those. So it's like, well, you don't immediately need it, but if you have to take calculus, this is one of those things that you want to kind of save in your memory. So the intermediate value theorem, it kind of, the way it's worded is kind of confusing, but it actually sort of makes sense when you think about it. So it says if a and f of a, so that's just saying that we have some point here, and then b and f of b, so that's just giving us another point here. If they are on the graph, and they're not equal to each other, so it's not like a constant line, it's not a flat line, then it's just saying, okay, there has to be a point in between there. And we know that because our polynomials don't have gaps. So there has to be some point in between those 2 points. We don't know where it is. It's just we know there has to be something because we have to be able to connect those 2 points. Now, the second part of the intermediate value theorem says that, okay, we have these numbers a and b, and a is less than b. So specifically as we have in this picture here. So if a is less than b, and we know that these are not equal to each other, the y values are not equal, so it's not a flat line, then in this interval, so in the interval connecting these 2 points, let me actually do that by highlighting. It says in between these two x values, we have to then hit every y value between those two y's. That's what it's saying. So it says in the interval a comma b, f takes on every value between f of a and f of b. It's just saying we have to hit every possible y value in order to connect those 2 points together. That's what the intermediate value theorem says, and it makes sense when you look at it graphically. Like, in order to connect those, yes, they're going to have to hit every y value in between there. So essentially, this is just saying that, okay, we have something that's continuous, that there's no gaps. And that's a very important thing when you get to calculus, that you're working with continuous functions. And a side effect of the intermediate value theorem is that this helps you determine if there's a zero. So if like a was a negative number, or I shouldn't say a was a negative number, let's say f of a, the y value at a was negative, and the y value at b was positive, and let me draw, let's say, instead of what we see here, we have a and b, but let's say f of a was here and f of b was here, instead of the picture that we have. Well, the intermediate value theorem says that these must be connected in some way. And the only way to possibly connect something that's negative and positive means you have to go through zero. So the intermediate value theorem says there has to be a zero in between there, because otherwise there's no other way to connect them. So that's like a corollary of the intermediate value theorem and related to zeros. This last line about that fact is useful when you're trying to find zeros, because when you're trying to find zeros, when you get to 3.4, you're basically looking for function values. You're just plugging in numbers and then seeing what the y value is. And so knowing that if you say you plugged in an x of 2 and you got a negative and an x of 3 and you got a positive, that tells you, okay, I need to plug in a number between 2 and 3 to find where my zero is. So it kind of helps you deduce where the zeros are when you're trying to find zeros of something that is not easily factorable. So that's essentially the intermediate value theorem, and it does pop up again in calculus, because a lot of times in calculus what you're doing is you're actually finding zeros, but you're finding it in a different way. You're looking for minimum and maximum points, and you do that by finding zeros. And so finding zeros actually shows up a lot in calculus. And so that's where this connects. But you don't have to really use it. It's more of kind of like, it's just a way of codifying logic, essentially, where it's like mathematicians are like, okay, logically we know this is true, so we're going to make a theorem out of it. And so that's what they did.